Hello, welcome to this lecture series on chemical kinetics. In my last lecture, I gave the expression for Arrhenius equation. Today, I like to continue some of the important informations about the Arrhenius equations. Okay, let's get started. So last class I have told you that when temperature of a gas phase reaction increases by 10 degrees Celsius, the number of collision increases by 200 to 400 times, but experimentally it was observed that the rate increases only by 2 times or 3 times. Okay, so what does this indicate is that Arrhenius gave explanation for that. According to Arrhenius, not all collisions are fruitful collisions. Not all collisions are fruitful. Okay, what is meant by that? According to Arrhenius, suppose we have two reactant molecules. Let us assume the energy of the reactant molecules, okay, it is less than some minimum energy required for the reaction, say activation energy. Okay, the energy of the molecule, suppose if it is less, okay, energy of the molecule is E and the value of E is less than the activation energy. If these molecules undergo collision, okay, then that collision does not give any product. No product. Collision will occur, but you will never get product. Why? Because the energy of the molecule, right, which is undergoing collision, right, is less than the minimum energy required for the reaction. Okay, so when you increase the temperature by 10 degree, no doubt number of collision increases. But the point here is not all collisions are fruitful. Okay, if energy of the colliding molecule, if it is less than the activation energy, those collisions are not, it's absolutely waste. It's an unfruitful collision. Whereas if the reactant molecules have energy, suppose reactant molecule have energy, if it is equal to the activation energy or greater than that, okay, if energy of the molecule, if it is equal to or greater than the activation energy, then if these reactant molecule undergo collision, yes, they form product. They form product, and these collisions are called fruitful collisions. Okay, collision which leads to product, okay, is called a fruitful collision. So what does this indicate? It clearly tells that not all collisions are fruitful. So the point that we have to note here is the rate constant of reaction, okay, not only depends on number of collisions, right? See, suppose I'll take some term here A, and this term will take care of number of collisions. Okay, and we need another term which will tell you what fraction of active molecule present at a given temperature. Okay, so this term will take care of number of collisions. The second term will give you what fraction of active molecules, at temperature T. Okay, so if you know this value and if you multiply with A, you will get the rate constant. This is the argument given by Arrhenius. How to find the fraction of active molecule present at temperature T? For that we can use Maxwell-Boltzmann distribution. So from Maxwell-Boltzmann distribution, it was found that the fraction of active molecule at temperature T is e to the power minus Ea by RT. So this will give you the fraction of active molecule present in the system at a given temperature T. What is meant by that? Listen, if molecule have energy greater than or equal to Ea, those molecules are called active molecules. Okay, if molecules have energy greater than or are equal to EA, those molecules are called active molecules. Okay, so at temperature T, what fraction of active molecule present in the system, that you can calculate by using this expression. This expression we obtain through Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution. Okay, so this is the information that you have to keep in mind. Okay, and this is the modified form of Arrhenius equation. K is equal to A into e power minus EA by RT. Okay, now as I said before, as I said in the last lecture, that this A, the Arrhenius parameter A, okay, is nothing but K max. K max means the maximum rate constant possible, okay, for a particular reaction, right? And you know very well, this K max can be achieved, right, by increasing the temperature to infinity. Okay, you know very well, when 1 by T becomes 0, then only you will get the maximum rate constant. When 1 by T will become 0, if T approaches infinity, then 1 by T becomes 0. So if you go to very high temperature, infinitely high temperature, then all collisions will give product. Okay, because if you go to very high, infinitely very high temperature, all molecule will cross the activation energy. Okay, so A, the Arrhenius parameter A, or the pre-exponential factor A, right, is nothing but equal to the rate constant, maximum rate constant possible for the reaction. Okay, that is why the unit of A is exactly same as the unit of the rate constant. Okay, so unit of A is equal to the unit of rate constant. Okay, this is a very important point, keep this in mind. Then if suppose if you take a first order reaction, right, for first order reaction, okay, the unit of rate constant, unit of K for first order reaction is second inverse. Therefore the unit of A is also second inverse. And you know very well, second inverse is the unit of frequency. So for first order reaction, this A can also be called as frequency factor. Okay, A is called as frequency factor. Right, for all other reactions, right, A should be called as pre-exponential factor. Okay, yeah, that is another important point you should keep in mind. Then note, see this Arrhenius equation, that is K is equal to A into e power minus EA by RT, right? This Arrhenius equation is not applicable, right? It is not applicable for number one, for radioactive disintegration reactions. Radioactive disintegration reactions. Okay, you cannot apply Arrhenius equation to radioactive disintegration reaction. See, you know very well, all radioactive disintegration follow first order kinetics. Okay, though these reactions belong to first order, we cannot apply Arrhenius equation to this. And second one, Arrhenius equation is not applicable even for zero order reactions. Zero order reaction, we cannot apply the Arrhenius equation for zero order reaction. Okay, it's a very important point, keep this in mind. Right, then what happens if activation energy of a reaction is 0? Okay, before going to tell you what happened when activation energy is 0, let me give you how to understand this activation energy through potential energy diagram. okay, are also called energy profile diagram. Suppose I'll take some reaction A plus B, A in gas phase, B also in gas phase, they collide and form some product. So it is a gas phase reaction, product also in gaseous state. Okay, now I am going to draw the energy profile diagram for this reaction. Energy profile diagram, okay, or potential energy diagram. Yeah, so what I'm going to do, I'm going to plot potential energy, okay, in y-axis. Then in x-axis I'm going to plot some reaction coordinate. Reaction coordinate means any coordinate that changes during the reaction. It may be a bond length, it may be a bond angle, okay, or it may be a dihedral angle, whatever it is. Reaction coordinate means the coordinate that should change during the reaction. Okay, so if you plot potential energy of the species present in the reaction with the reaction coordinate, okay, what type of graph we'll get? That graph is nothing but potential energy diagram. Okay, see, this is the average energy of the reactant molecule. Let us assume this is the average energy of the reactant molecule. Let me write R. I have two reactant A and B. Take the average. The average energy of the reactant molecule is this. Now what will happen during the reaction, right? The reactant molecule gains energy and reaches a maximum and then forms the product. Suppose assume that this is the product energy, average energy of the product. Okay, so reactant never form product directly like this. This is possible, this path is possible only if activation energy is 0. If activation energy is 0, then reactant directly form product, but this is not happens in many cases. For most cases, activation energy is not equal to 0. Okay, and in many cases actually activation energy is greater than 0. So some energy is required for the reactant molecule to form product. Okay, and if you trace the path, right, if you draw the potential energy, variation of potential energy with respect to reaction coordinate, actually we get many paths. So this is path 1 for the reaction, this is path 2 for the reaction, this is path 3, all give same product, path 4, like that. Your starting average energy is same, the first average energy of the product is same for all the path. What I'm trying to say is a reaction follow many paths. Okay, this is path 1, this is path 2, this is path 3, this is path 4, like that we have many paths. Okay, we actually consider the minimum energy path. So this one is called the minimum energy path. Minimum energy path. Okay, the energy that is acquired by the reactant molecules to reach this barrier, this top, okay, is called the peak point is called actually energy barrier. To reach this energy barrier, reactant molecule must acquire some energy. That energy is what we call as activation energy. So what is activation energy? It is the minimum energy, or it is the energy acquired by the reactant molecule to reach the potential energy barrier of minimum energy path. Okay, let me write here. So what is the activation energy? Definition: activation energy is the energy acquired by the reactant molecules, the energy acquired by the reactant molecules to reach the potential energy barrier, of minimum energy path, of the reaction. Okay, this is the definition for the activation energy. For other path also, see, we have potential energy barrier for other path also. Okay, but these energies are not actually activation energy, they are all above activation energy. But what remember it is, if molecule comes here, it comes here, right, those molecules are also called active molecules. Okay, because they have energy above activation energy. Okay, now, so this is the meaning for activation energy. Activation energy is the energy acquired by the reactant molecules to reach the potential energy barrier of minimum energy path, okay, in a reaction. Okay, now, so now you know what is meant by activation energy of a reaction. Okay, then next important point, what happens if activation energy is 0? Okay, if EA equal to 0, what will happen? You know very well, rate constant equal to A into e power minus EA by RT. If activation energy is 0, then K become equal to A into e power 0. E power 0 is 1, so K is equal to A. Right? If A term, okay, take care of number of collisions, then what does it indicate? All collision leads to product. If activation energy of reaction is 0, all collisions are fruitful collisions. Okay, only in this case, if temperature is increased by 10 degree, okay, the rate also increases to 200 to 400 times, because activation energy is 0 for this reaction. Right? Then second important point, if temperature of the reaction approaches infinity, what will happen? If I go to very high temperature, and in this case activation energy is not 0. Activation is non-zero, some activation energy is there, but temperature approaches infinity. Right? In this case, see, K is equal to A into e power minus EA by R. Now in the place of T, I'll put just infinity here. You know very well, R into infinity is infinity, something by infinity is 0, so again you'll get the e power 0, and I'll get A again. What does this indicate again? All collisions are fruitful collisions. Activation energy is not 0, but all collisions are fruitful collisions because we have reached infinitely high temperature. Okay, when you go to infinitely high temperature, all reactant molecules, okay, become active molecules. Right? Under this condition, right, when temperature approaches infinite, all reactant molecules become active molecules. All reactant molecules become active molecules. Okay, therefore all collision leads to product. Okay, then what happens if temperature approaches 0 Kelvin? This is another important point we should keep in mind. If temperature approaches 0 Kelvin, what will happen? See, rate constant K is equal to, according to Arrhenius equation, A into e power minus EA by RT. In the place of T, I'll put 0. So A into e power, and here also I am assuming activation energy is not 0. We have some activation energy. E power minus EA, we have some activation energy R. Then in the place of T, I'll put 0. 0 into R is 0. Something by 0 is infinity. So K is equal to A into e power minus infinity. Or K is equal to A into e power minus infinity can be written as e power 1 by e power plus infinity, or K is equal to A into 1 by e power infinity is infinity. 1 by infinity is 0. Therefore K becomes equal to 0. What does this indicate? It indicates that when temperature goes to 0 Kelvin, okay, no molecule get active molecules. No molecule become active, right? So what does this indicate? When temperature approaches 0 Kelvin, Okay, no molecule in the no molecule of the reactants, no molecules of the reactant are active. No molecule is active. So all collisions, even if at all occurs, all collisions are absolutely unfruitful collisions. So reaction never happens. Okay, yeah, so keep this point in mind. Then see, what is the suppose if I know activation energy for a reaction. Okay, we have calculated or we have determined activation energy for a reaction through some method. If you know activation energy, okay, you have some advantages here. Listen, once you know activation energy for a particular reaction, and if you know the rate constant of a reaction at some temperature T1, if you know the rate constant of the reaction at some temperature T1, you can calculate the rate constant of the reaction at some other temperature T2. Okay, you can calculate K2. See what I'm trying to say? If activation energy is known for a reaction, then if you know the rate constant at some temperature T1, then you can calculate, or you can very easily find out the rate constant at any other temperature. How? Yes, we can use this expression. So this is Arrhenius equation in log Baseton form. Log K Baseton equal to log A Baseton minus EA by 2.303 into R into T. Okay, so I have written the Arrhenius equation in log Baseton form. Okay, what I'm going to do, at temperature T1 you put K as K1. Okay, so at temperature T1 we can write this as log K1 Baseton equal to log A Baseton minus EA by 2.303 R T1. Similarly, at temperature T2, okay, log K2 Baseton equal to log Baseton A minus EA by 2.303 R T2. Listen carefully, as we change the here we are changing the temperature, but Arrhenius parameters A and EA remain same. That means A and EA are independent of temperature here. Okay, or otherwise I can say that the chemical reaction that we have taken here is an Arrhenius reaction. Right, now I'll take this as equation number 1, this is equation number 2. I'll subtract 1 from 2. Assume that the temperature T2 is greater than T1. If T2 is greater than T1, you know very well, as temperature increases, rate increases, so rate constant increases. Okay, in general. So compared to K1, K2 value is high. Therefore, I am going to subtract this lower value from the higher value. Okay, so log Baseton K2 minus log Baseton K1 equal to, we have subtracted the left hand side. In right hand side, if I subtract, log A cancel, so we have minus EA by 2.303 R T2. This is the first term we have. Then minus of this, minus of minus become plus, you will get EA by 2.303 R T1. This we can write it as log A minus log B can be written as log A by B. So we can write this as we can write this one as log Baseton K2 by K1 equal to, here I'll take EA by 2.303 R as common. So we get, I'll write the positive term first, 1 by T1, then minus 1 by T2. Okay, or you can also write this as log Baseton K2 by K1 equal to EA by 2.303 R into T2 minus T1 by T1 into T2. Okay, so using this expression, if you know rate constant at a temperature T1, at temperature T1 rate constant is K1, and if you know activation energy, then you can calculate the rate constant K2 at any other temperature T2. Okay, yes, so keep this in mind, very important. Using this expression, you can calculate the rate constant of reaction at any other temperature, okay, at any given temperature, provided the activation energy of the reaction is known. Okay, yeah, so this is some important points regarding Arrhenius equation. Okay, yeah, I stop here. We'll continue this in the next class. Thank you.